his doctoral degree in theoretical high energy physics from Banaras Hindu University, Varanasi in 2014. He has a rich postdoctoral experience from IISER Kolkata, Banaras Hindu University, Sun Yat-sen University in Guangzhou, China. And while he was at IISER Kolkata, I and he had a short overlap. Uh, that's that's uh, that's very nice to uh, be introducing him for this session. His research interests encompass the quantum field theory, PT symmetric and supersymmetric quantum mechanics, and chiral anomaly. He has published many peer-reviewed articles, and with this introduction, I request Dr. Shukla to tell us about emergent PT symmetry and breathers.
Thank you, Subhimal, for this nice introduction. So first of all, I would like to thank the organizer for giving me the chance to present a part of my research work at such a great platform. So in this talk, I will discuss briefly about the PT symmetry, supersymmetry, and its application, as well as I will briefly discuss about the breathers, which are the solitonic solution of TdV equation. So this is the plan of my talk. Initially, I will give a brief introduction about the parity time symmetry that is called PT symmetry and its other application. Together with, I will also talk about this supersymmetric quantum mechanics. Then I will take a simplest example of free particle in infinite box, and by using the isospectral deformation, which is a powerful technique in supersymmetric quantum mechanics, I will try to connect this free particle to the KdV equation, and we will try to give a solution which is called a breather solution, and we will try to connect this breather solution to the free particle in infinite box. And then I will generalize this free particle to a generalized potential where we will I will use this shape invariance to obtain the energy eigenvalue, and in this generalized potential I will show that there exist zero-bit resonance states, and finally I will conclude my talk. So as far as this PT symmetry is concerned, so all of you know that this in conventional quantum mechanics, all the physical observable have to be Hermitians so that its eigenvalues are real. But Bender has showed that it is not necessarily that the operator should be Hermitian. If the operator or Hamiltonian is PT symmetric, then we can also obtain the real energy eigenvalue of corresponding to that operator. So PT symmetry means if x going to minus, this is a kind of symmetry where if Hamiltonian remains invariant when x going to minus x and I going to minus I, then it is called the PT symmetric Hamiltonian. For example, here I have a general Hamiltonian, which is p square plus x square into I x to the power epsilon. Here we can see that when epsilon is greater than or equal to 0, this Hamiltonian will have a real energy eigenvalue, and when epsilon is less than 0, it will have the complex eigenvalues, whereas when epsilon is equal to 0, since this term is 1, I times ix will be 1. So this Hamiltonian will be is a Hermitian matrix. This Hamiltonian can be pictorially represented as this. Here we can see that this epsilon equal to 0 represents a PT boundary, means it breaks two regions of the PT symmetries. One region is PT unbroken and second region is PT broken region. Here we can see that when epsilon is less than 1, so this PT symmetry will be broken, and when epsilon is greater than 0, then this region belongs to the PT unbroken region. So the PT symmetry has many applications in optics, photonics, as well as it has led to develop the PT symmetric and supersymmetric laser. And further, it has also it has been shown that light stops at exceptional point where this PT symmetric formalism has played a major role in that. It has been, this paper has been published in PRL in 2018. So now let us talk about this formalism of supersymmetric quantum mechanics. So the supersymmetric quantum mechanics interrelates the spectra of two different Hamiltonian, this H plus and H minus, which have the potential V plus and V minus, and these two potentials are called supersymmetric partner potential, and it can be obtained by using W square plus minus W prime. This W prime is the derivative with respect to X, and Wx is the superpotential in the supersymmetric quantum mechanics. And this Hamiltonian H minus and H plus can also be obtained by A dagger A and A dagger, where A dagger A is just like a creation and annihilation operator, which is given as following. So one of the important feature of supersymmetric quantum mechanics is that if we know the superpotential in the supersymmetric quantum mechanics, then we can obtain the ground state, as we all know we do in the basic quantum mechanics. This formalism is also applicable here. So this psi naught is the ground state, and if you know the superpotential W, then we can obtain this psi naught by using this expression. On the other hand, if you know the ground state of the Hamiltonian, then we can obtain the corresponding superpotential. So in this supersymmetry, broken and unbroken depends upon the nature of Wx, means W is the superpotential, and if the asymptotic value of Wx at plus and minus infinity is of opposite sign, then we can say that supersymmetry is unbroken. And if W tend to asymptotic value has the same sign as x equal to plus infinity and x equal to minus infinity, then we can say that supersymmetry is broken. So now, as I have said that this supersymmetry formalism interrelates to Hamiltonian. Here we can see it pictorially, except the ground state. Means ground state will not be supersymmetric partner. For example, in this figure we can see that this is the energy spectra of Hamiltonian H minus, and this is energy spectra of Hamiltonian H plus. So except ground state, every energy eigenvalue is same, and we can move around from one energy spectra to another energy spectra by applying the creation and annihilation operator. Similarly, we can also obtain the this kind of relation in terms of wave function. Means if we know the wave function for H minus, then we can get the wave function for this H plus Hamiltonian by using this formula, and just we have to apply this creation and annihilation operator. And if you want to understand the supersymmetric quantum mechanics from the scratch, you can go through this paper by Fred Cooper, Avinash Kare, and Sukhadme. This is a physics report. It is very beautifully written in simple language. So now the supersymmetric quantum mechanics has one of the powerful technique, which is called isospectral deformation, which is used to generate a class of potential which has identical spectra. For example, if you have superpotential Wx, you can always generate a deformed superpotential W tilde. You have to use this transformation. This W tilde will have the generate the potential V plus by using this formula, provided this condition has to be satisfied. Means this W tilde, when we know the W tilde, we can always generate V minus and V plus, and V minus will be unchanged when this condition, which is called Bernoulli equation, it is satisfied, and we can obtain the different potential V plus by using this formula. So now there is also one of the important technique in supersymmetric quantum mechanics, which is called shape invariance. By using this method, we can obtain the energy eigenspectra of any potential. For example, these two, for example, if you have potential V minus and V plus, these two potential, as I have discussed, these two potential is called supersymmetric partner potential. So if we know the energy spectra of one potential, then we can always get the energy spectra of another, the supersymmetric partner potential, provided they have to be the shape invariant. Shape invariance means if somehow by using some transformation, we can convert this V plus in terms of V minus plus some constant, function of constant. It has not to be the function of X, it has to be function of constant. Then we can always get the energy spectra of this P plus like this, where this P plus and V minus are called shape invariant potential. And this formalism has been discussed very beautifully in this Stein paper, which has been published in QIQT, which is an old paper. It is very, they have given some simple shape invariant potential, and they obtained the energy spectra corresponding to them. So now I will come to our work. So we have taken this free particle, and we have connected this free particle to the KdV equation. For example, we all know that the Hamiltonian for the free particle is given by this, and the corresponding superpotential will be a constant, because this constant can always be absorbed in the ground state energy. And by using the Bernoulli equation, this superpotential leads to a new superpotential Wx lead to a new superpotential, where we have to use the Bernoulli equation, and it will provide a new superpartner potential V plus tilde, which is given by this, and the ground state corresponding to this potential, this superpotential can be obtained by using this formula. So the ground state is given by this, and where this x1 and x2 are the boundary. So as I previously mentioned, that the supersymmetry will be unbroken when this ground state must be the same as the ground state of this Wx. Means we have a superpotential which is different from this, and the ground state of Wx is equal to A has to be same as the ground state of this W tilde. And when we apply this condition, then we obtain A is equal to I times A, where A is a real constant. So this form of constant A is equal to IA also emerges naturally when we use the boundary condition, where A and C both are not equal to 0, and the this wave function can be given as this. And here we can see that the constant A has a kind of relation with the boundaries of the potential. Means A is equal to I by x2 minus x1, where x2 and x1 are the boundaries of the potential. So now this, when we expand this superpartner potential by putting A is equal to IA, then we will obtain this P plus is equal to this. And here it is necessary that this constant C is not equal to 0 when we take C is equal to 0. So it will be simply cosec square AX, which is kind of potential in a bell. Means the partner potential for the free particle, which represents potential in a bell. So, but we can always think that C can be any general. It can be real, it can be complex. So we are taking this complex C, and when we take this complex C value, so by using the boundaries condition, we will get this condition, and where it shows that since C is constant, then x1 and x2 means boundaries also has to be constant. So this says that this space has to be constant since we have what we did. We have taken a free particle and then we have applied the isospectral deformation and we generate a new super partner potential. So when we take C as a complex, then the space also has to be complex. So till now, what we did, the difference between x2 minus x1 has to be m pi by a, where is m is an integer, and the 1D infinite potential well with arbitrary width is generalized to the infinite 1D potential well, which is where the well in the complex plane, and the potential V minus can correspond to different infinite well subjected to different combination of m and a. Since there here this difference between x2 minus x1 is m pi by a, so here we can see that this boundary is quantized. So this means this will represent potential width well which has quantized width. Okay, so now we have expanded this potential V plus in terms of xi and eta, where xi and eta are new variables, which is written as following. And so here we can see that this potential V plus tilde is PT symmetric, but we have to generalize, we have to redefine the coordinates. For example, here this when xi is equal to minus xi and eta is equal to eta, and I goes to minus I, then we can check that this whole potential is PT symmetric. For because this cos is even function and this sine is odd function, and when this I goes to minus I, then ultimately it changes the sign of this factor. So ultimately V plus will remain unchanged under this PT symmetric transformation. So here the PT symmetry will not be x going to minus x, I going to minus I. Here the PT symmetry will be psi going to minus xi and eta going to eta and I going to minus I. Okay, so this is kind of emergent PT symmetry, and this is the plot of the real part and imaginary part with respect to the real x, and this is the plot of real part and imaginary part of the potential with respect to imaginary x. Here we can see that in the real part of real value of x, this imaginary and real parts oscillates with a particular period. Okay, and whereas this imaginary part is kind of confined in a region. So so now we will connect this potential as a solution of KdV equation, where we have to again regeneralize this parameter xi. So when we take xi is equal to 8 times x plus 4 AQT, then we have seen that this potential is a solution of this KdV equation module a constant set. So as I have shown this in this plot, this real and imaginary part of the potential is periodic in real value of x, and this real and imaginary part of potential is kind of confined when we plot with respect to imaginary value of x. So which is kind of behavior of a breather. So what is a breather? Breather is a special kind of solution of KdV equation which is periodic in space and time. So here we have taken xi as a space. So this potential will behave like a breather. And breathers have also observed in DEC and optical waveguide, and a similar kind of solution also exists in focusing KdV equation. This is defocusing type KdV equation, and this is focusing type KdV equation. You have to see that there is a sign change in both the equation. So okay, so this kind of solution also exists in the focusing KdV equation, where the time delay analysis has been performed in this paper. So furthermore, this superpotential W is equal to A times cot xi plus I eta satisfies focusing and defocusing modified KdV equation. So this is modified KdV equation, which is different from this KdV equation. Here we can see that these two equations are interrelated when we put V is equal to IV. This equation, when we put V is equal to IV, this will convert into this. So the QIQT equation relating to the potential and superpotential can also be identified as a corresponding Mura transformation. This is a Mura transformation where U is the solution of KdV equation and V is the solution of MKdV equation. So we can say that we have two distinct KdV solutions which has been obtained from the isospectral potential. Okay, so now we want to generalize this potential. So for that, we will go to the complex plane. So in complex plane, the Schrodinger equation can be written as this, where this is a two-dimensional Laplacian operator, and K square is equal to will be equal to E, which is energy of the energy in this case. So for a particular solution, we have taken a particular kind of solution like this, where K tilde is in general complex. So when we put this, so this Schrodinger equation will convert into this kind of Schrodinger equation. So now we will generalize. We will propose a new superpotential, which is quite different from this earlier superpotential, which is minus A cot A x into C. So now we will take this kind of superpotential, where this has two parts. First one is A cot alpha x plus C. Second one is B tan alpha x and C, where A, B, and alpha are the constant parameter. So when we have superpotential, we can always generate the corresponding superpartner potential, which is in this case will be V tilde A minus and V tilde A plus. So here one of the important things have to be observed, that when A is equal to B is equal to alpha, so this term will be, so this term and this term will be 0, and what will be the remaining term will minus 4A square. So which is kind of earlier potential. In that case, it was A minus A square, but here we are getting minus 4A square. It is kind of scaled one, and the partner potential will convert into this 2A cos x square xi plus I eta, which is kind of same as the earlier V plus tilde, which we have seen. So, but when A is not is equal to B, is not is equal to alpha, then we can see that V minus B1 minus tilde is shape invariant. These two potentials are shape invariant with each other. This means by using a kind of transformation, A going to A plus alpha and B going to B plus alpha, we can convert V1 tilde in terms of V1 tilde minus, where this is only the constant term. There is no x means variable is involved. So we can always obtain the energy spectra of V1 tilde potential, which will be by using the shape invariant formalism, which will be given by this. So now we have to choose a particular kind of ground state. So in this case, we have chosen ground state means n is equal to 0. In this case, n is equal to 0. So we have chosen this A plus B is equal to A plus B whole square is equal to K tilde square, where K tilde is complex, and when we take this kind of ground state, then this En will be converting to this. It is quite easy to check here. So one of the important thing to be observed here, that when K real value of K tilde real is equal to minus 2n alpha, so these two terms will be cancelled out and we will left with only the real energy eigenvalue. So earlier, I have to forgot to mention that since this energy eigenvalue is complex, it is not real. Here one can see that. So this when energy eigenvalue of a potential is complex, then in that case PT will be broken. PT symmetry will be broken. So here the PT symmetry is broken, but when we put k tilde real is equal to -2 n alpha, then these two terms will be cancelled and we have real energy eigenvalue. So this represents, this kind of states represents the zero width resonance state. Means when we are in broken phase, then we are getting the real energy eigenvalue. So that condition will
Small
be,
interruption.
yeah,
Just remember that you have about a couple of minutes more.
okay. So it is okay. So this state will be called zero width resonance states. Okay, and so this is kind of conclude my talk. So what we did in this talk, so the isospectral deformation of a free particle has enabled natural generalization of quantum system to complex potential through a general boundary condition. As we have seen, we have not chosen this constant C is equal to 0. We have taken the value of C as a general constant. It can be complex. So we have taken the complex value of C. So with appropriate parametric identification, the isospectral potential has found out to be PT symmetric. During this process, the complex potential satisfy the QDB equation where both real and complex parts shows the breather behavior. And for a particular choice of ground state, will lead to the broken sector of PT symmetry, and in that broken sector we will have zero width resonance state for a particular choice of KT. Okay, that's it from my side.
There are a couple of questions in the chat box.
Yes.
First
So
one, both from Lakshmi Prasad Nayak. The first one is how PT symmetric quantum mechanics and SUSY quantum mechanics is different.
So in the PT symmetric quantum mechanics, it basically deals with which I told in the talk that the PT symmetric quantum mechanics, the Hamiltonian need not to be the Hermitian. The PT symmetry, if Hamiltonian is PT symmetry, symmetric, then we will have the real energy eigenvalue. Whereas in basic quantum mechanics, what we have to this Hamiltonian has to be Hermitian. So the supersymmetric quantum mechanics is quite different field than the PT symmetric quantum mechanics. So in supersymmetric quantum mechanics, there is no such condition that this PT symmetry, the Hamiltonian should be PT symmetry. Okay, so it is quite different. Both PT symmetry quantum mechanics and supersymmetric quantum mechanics both are different branches, and they have been merged to be applied to the more fascinating fields. And second question is, what is implication of broken and unbroken PT supersymmetry? Okay, so as I have said that when PT symmetry is broken, so you will have the energy eigenvalue will be complex. Whereas in unbroken PT symmetry, the energy eigenvalue will be real. And as far as this broken and unbroken SUSY symmetry is concerned, so so when the supersymmetry is broken, so I think you have remembered. Let me go to that point. See this when supersymmetry is broken, then the ground state will be not unique. Means you will have multiple ground state. But when supersymmetry is unbroken, then ground state is unique. Okay. So this is a basic requirement of unbroken supersymmetric quantum mechanism. Means the ground state should be unique. And when supersymmetry is broken, the ground state is not unique. So this is the main difference between broken and unbroken supersymmetric quantum mechanics.
Okay, if there are no more questions, we can move on to the next talk.
Okay, 1 second. Okay, thank you very much.
Thank you. Thank you, Dr. Shukla. So our next speaker, Shubham Kumar, he also has a past connection with IISER Kolkata. He was a research intern here before he moved on to pursue his doctoral degree at the International Center for Quantum Artificial Intelligence for Science and Technology in Shanghai University. He's working in the field of neuromorphic quantum computing, and his research interests include superconducting circuits, open quantum systems, quantum simulation, reservoir quantum computing, and quantum neural networks. He wants to use his knowledge and expertise towards merging quantum and neuromorphic computing in order to realize efficient and powerful devices. So with this, I request Shubham to tell us about a topic of his interest in the next half an hour.
Okay, thank you for having me here. Good evening to all. First of all, I would like to know if I'm audible or not.
Yes, you are audible.
Okay, thank you. So I'll be starting my talk. Let me show you my screen. Is my screen visible?
Yes.
Okay. So I'll be talking about one of my works, which was recently published in PRA, entitled as Entangled Quantum Memristors, which is specifically, we explored the bipartite entanglement of quantum memristors in superconducting circuits. So starting from the introduction of my group, here is my boss, who is Professor Enriquez Blanc, the group leader. These three are the postdocs with whom I have worked with, Gabriel Francisco and Francisco Cardenas. And the last one is Narendra, who is my good friend and a PhD student along with me in the center. So the outline of the talk is as follows. I'll start with explaining what is neuromorphic computing. Then I'll move on to explaining what is neuromorphic quantum computing, what it is, why do we want to approach it, and how are we going to approach it. Then we will move on to the memristors, which are basically classical and quantum. I'll be explaining both of them. Then I'll be explaining the memristive element in a Josephson Junction, which is the basis of the device which I'll be introducing in this talk, which is known as a superconducting quantum memristor. And the main part of the talk is the entanglement of these quantum memristors. I'll be explaining their characteristics and how can we move towards neuromorphic quantum computing using such devices. So neuromorphic computing is basically refers to the implementation of brain-inspired devices at the software and hardware levels for applications to digital and analog computation. As the name suggests, the goal of this paradigm is not to efficiently simulate the brain synapses or things like that, but what we actually want to do is realize biological computation in a practical computing system in the current state of the art approaches being used in the current scenario. So the devices which we can implement using such paradigms is neuron and neural networks. So neuromorphic quantum computing basically refers to the implementation of brain-inspired neuronal architecture on quantum hardware and software level to design integrated quantum devices. And there are basically, the first question is, why do we want to use it? And these are the possible answers, in which we first want to speed up computation, and we want to apply this speed up into AI and machine learning applications. Furthermore, we want to gain more insight into neural systems for applications to memory storage, and also to design dense architecture such as a quantum neural network. Secondly, we want to answer how are we going to approach this paradigm. And basically, there are two approaches, which are digital and analog. On one hand, the digital approach comprises of gate-based quantum circuits in which we can mimic neural algorithms, for example, a quantum neuron. And this actually requires the training of variational circuits, and using which we can apply these things to simulation of memristive systems. The second approach is the analog one, where we basically utilize the dynamics of physical systems, for example, a quantum oscillator. And this is based on adiabatic dynamics of the physical system. The application of the analog-based approach has been recently achieved in reservoir quantum computing, where the reservoir dynamics, which is implemented using the quantum system, has been applied to neuromorphic architectures. So firstly, introducing the classical memristor. Here is a graphical representation of the memristor, which was experimentally realized in 2008 by HP Labs. And it actually consists of a semiconductor, which has a doped and undoped region. And using an external voltage, we can actually increase or decrease the doped or undoped regions, basically the width W. So how this happens, and this mechanism actually introduces a memristor behavior in the system. So the memristor actually is a resistor with memory, which is characterized by pinched hysteretic signatures and has bistable resistance states, which can be used to store information. In this system, this can correspond to the two different configurations of W, which can be achieved by applying an external voltage. This type of system has been used widely in classical neuromorphic architectures. And mathematically, memristors are described by state-dependent nonlinear Ohm's law, which is given by, sorry, this equation is a little bit down. So this actually relates the current with the input voltage using a nonlinear function, which is a function of x, v, and t, which are the state variable, voltage, and time. And this describes the nonlinear response of the system, where the dynamics of the state variable takes this form and produces a nonlinear curve. This dynamics describes the dynamics of the internal variable, which corresponds to the microscopic reconfiguration, using which we can achieve different stable states. So the IV characteristics looks like this, which is not a linear resistor, but nonlinear and also pinched hysteresis curve. And this curve is pinched at 0. So this is a qualitative trait of a memristive system. So the mechanism of memristivity is traced to the microscopic atomic rearrangement in an electronic component. And such kind of rearrangements can happen in presence of an external bias. And this corresponds to a stable atomic or molecular configuration or stable states. And this kind of response of the physical system is well explained by Kubo response theory, for which I have provided the reference. And the derivation of memristive behavior, the derivation of memristive equations has been carried out in this reference. If one is interested, he or she can look into it. Now, a little bit history about memristive systems that have been engineered and discovered in quantum systems. Firstly, it was the superconducting memristors, which was published in 2014, which was a seminal paper by Piotta and Deventra, in which the guys explored the memristive element in a Josephson junction. And this was followed by 2 papers from the group of my professor, who's my PhD supervisor, Professor Enrico Solano. And it was proposed that quantum memristors can be engineered in superconducting circuits using external feedback, classical feedback. And also there was another work in which the quantization of the superconducting memristors was followed. After this, we have proposed the bipartite entanglement of quantum memristors, which was recently published in PRA. And following which we have explored the tripartite entanglement in quantum memristors, which is currently under review. And in parallel, there have been also some works in quantum photonics where memristors have been engineered. This is the first work in quantum photonics, same from the group of my professor. And the second one is an experimental photonic quantum memristor, which was realized recently in Nature Photonics, published in Nature Photonics by the group of Philip Walter in Vienna. And currently we have followed up this work and we are working on the microwave quantum memristors. And we are currently preparing a manuscript. So now I would like to explain the quantum memristor. Memristors have been proposed in quantum regime using superconducting circuits and quantum photonics. So there have been 2 or 3 proposals, but in this talk, I'll be interested in explaining the 2 of them, which is more prominent. The first one is the superconducting one, which is the focus of my work. And the second one is the photonic one, which was experimentally realized. So both these 2 are schematic representation of the 2 devices. The first one comprises of a superconducting quantum interference device, which is basically a parallel connection of Josephson junctions in a loop. And this is connected externally to an inductance, which is not shown here, but this wire contains an inductive contribution to the system. And this is input with an external flux phi d. So this flux sets up interferences in this loop so that we can manipulate different current forms. And one of those current forms is memristive in nature, and we can produce a area here represents a beam splitter. A and B are the inputs from which photons can enter. And out of the 2 outputs, one of the output is used as a feedback. After measurement, we can tune the beam splitter using a feedback. So this work was recently published in Nature Photonics. So the focus of my work is the memristive element in Josephson Junction, and I would like to explain it in brief. So Josephson junctions have an intrinsic memory resistive character that originates from the transfer of Cooper pairs via quasi-particle tunneling. And mathematically, Josephson has predicted 3 kinds of current in a Josephson junction. Sorry, yeah. So these are the 3 forms of current, where the first one is the famous critical current, using which people design qubits. And the second and third terms are the quasi-particle currents, out of which the second term is the phase-dependent quasi-particle current. And this is the focus of our work. We can neglect the quasi-particle current contribution as the regime in which we will be working, we can cancel out the quasi-particle current. So the memristive element is the second term, which is the phase-dependent part of the quasi-particle current, which is given by this equation. And as you can see, it has a strong resemblance with the memristive current, memristive equation, where epsilon times GL becomes the response function, and it is known as the memristance of the device. The physical phenomena of this current can be explained in this figure, where I have shown the transfer of a quasi-particle, which happens after the breaking up of a Cooper pair on one side of the junction, and it's tunneling onto the other side. So as you can see, the Cooper pairs can break up into 2 quasi-particles, one of which can transfer into the other side by changing their spin state. And after getting transferred to the other side, the quasi-particle can combine with another free quasi-particle to create another Cooper pair. So this mechanism is actually a virtual transfer of Cooper pair via quasi-particle tunneling. And this leads to a memristive behavior in the junction. This is represented by this current. So in order to design a device in which we can have a strong memristive character, we need to have a system in which the second term can dominate over the first term. So for this purpose, we have a system like this, which is known as a superconducting quantum interference device, where we have two parallel connected junctions. And if we apply an external flux, we can set up interferences of currents in the circuits. And using some conditions, we can either cancel out one of the currents. So in this case, we want to cancel out the critical currents and produce a dominant cosine current to obtain a dominant Memristive behavior. So for this purpose, we have certain conditions which are given by these 2 points, where we should have a conductance asymmetry between the two junctions in terms of the band gaps of the junctions. And this relation was derived by Ambergawker and Baratov relation, which is a famous relation relating the band gaps with the responses of the junctions. And the second condition is that the external flux should be fixed to half a flux quantum, phi0/2, so that the phase difference between the two junctions should be equal to phi. And this will lead to equal and opposite critical currents. And when they interfere, they will cancel out completely. So this setup was introduced by Toyota and Triventra in a seminal paper in Bipartite in 2014. Following this, there was a proposal to quantize this complete system by introducing an external inductor, because since we have cancelled the Josephson current in this junction, we do not have a nonlinear inductive character in the system. And in order to have a complete quantum mechanical description, we also need an inductor. So for this reason, there was a proposal in which this loop was connected with an external inductor to make a quantized description of the circuit. So this is known as a conductance asymmetric SQUID, which is connected to an external inductor. And this is an equivalent circuit where we can see the different types of current contributions coming into one of the nodes, and out of which the quasi-particle current is the one which we are interested in because it has the Memristive character. The system can be effectively treated as a LC resonator coupled to a quasi-particle bath that induces the system's dissipation with a time-dependent decay rate. So the system and bath description is as follows. The total Hamiltonian of the quantum Memristor describing the interaction of the harmonic oscillator with the bath is given by this form of equation, where the two forms are given by the first form is the quantum oscillator, the harmonic oscillator, and the second one is the tunneling Hamiltonian, which is the focus of our work because it is due to the quasi-particles. And it can be derived using Fermi-Golden rule, using perturbation theory. And here we can see that T is the tunneling amplitude, U, V are the Bogoliubov amplitudes, which can be assumed to be constant in this case due to the regime we are working in. And R and L describe the tunneling process in the left and right side of the electrodes. HC represents the Hermitian conjugate of this part of the Hamiltonian. So the effect of the environment here corresponds to the tunneling of quasi-particles between the CS SQUID with the electrode forming the reservoir, and this leads to an energy relaxation of the quantum Memristor. So by using Fermi's Golden rule, we can actually derive the decay rate to take such a form, which describes the transition from an initial state to a final state, which are electromagnetic in nature. And this also is proportional to the quasi-particle spectral density. And these analyses have been carried out using these two references from G. Catalani and H. Brabant, where G. Catalani's paper was PRL in 2011, which explained in much detail the quasi-particle relaxation in superconducting qubits in presence of flux. And the second one is the single charge tunneling, from which we can actually derive these Hamiltonian, the tunneling Hamiltonian. The dynamics of the system can be described by a Lindblad form of evolution, which describes the decay induced by the quasi-particles on each oscillator. So since we are working in a quantum harmonic oscillator, we perform a two-level approximation to simplify the problem and use an adiabatic driving to fix the analysis into only two levels so that we can avoid any kind of jumps to higher states. So after this analysis, we can find that the the Lindblad form of Lindblad equation looks somewhat like this, where the first term is the usual commutator between the Hamiltonian and the density, and the last two terms are the ones describing the decay of the system, where CL are the collapse operators, which are dependent on the root of the decay rate and proportional to the annihilation creation operators. So we can derive that the decay rate takes the form given by this, where after performing a two-level approximation, we have that it depends on the 0 state and the 1 state. And the regime which we are working in is high frequency and low energy regime to avoid extra generation of quasi-particles. And in this regime, we can have that the quasi-particle spectral density becomes proportional to the frequency of the system. Furthermore, due to the flux quantization rule on the outer loop of this device, we can have that the decay rate takes this form, and it comes out that this is proportional to the cosine of the phase, external phase. And this means that by using the external flux, we can control the dynamics of the system. And this system will thus happen to be a flux controlled memristive device. So the hysteresis signature of the system has a decaying character. And once we apply an external flux, it shows a pinched hysteresis curve. And the pinched nature has been shown to be at 0. It has zero crossing nature, and hence it is memristive. The current and voltage dynamics with respect to time is shown in this figure, where one can see that these are decaying in nature. So following this, we have proposed the bipartite entanglement of quantum memristors to explore how the memristive behavior can be connected to the entanglement in the system. So this system is familiar in the sense that we use two quantum memristors and couple them with either an inductor or a capacitor. And in this figure, I have shown both of them, but in practically, we are going to use only one of either the capacitor or the inductor. So the total Hamiltonian of the system takes a form which comprises of two quantum harmonic oscillators and a coupling term, which can be either capacitive or inductive, depending on the coupling. Furthermore, after performing a second quantization, we can have that the system can be represented by this form, where the first term is a harmonic oscillator, the second term is a coupling, where omega 1 and 2 are the frequencies of each oscillator, and alpha and beta are the capacitive and inductive coupling. And in either case, one of them will be 0. So the open quantum dynamics of this system is simple and can be considered as an extension of the single quantum memristor, and is shown to be like this, where the decay rate has two parts consisting of quantum memristor 1 and 2. The decay arising from the first quantum memristor and the second quantum memristor. And the first term consists of the Hamiltonian of the combined system. So this actually represents a system of coupled quantum harmonic oscillators that are interacting with their local reservoirs. So the memristive characteristics of this coupled devices are rather non-trivial and more interesting than the single memristor case, in the sense that we obtain some features like this. This is his IV characteristics of the coupled system, in which we have plotted the IV characteristic of one of the quantum memristor, because what we have taken both of the memristors to be identical. So what we observe is that the hysteresis actually decays and revives after each oscillation. Not each oscillation, but after certain oscillations. And here I have shown that I have colored the curves where decay there happens to be a decay, then it starts to revive, and then it starts to decay again. For example, from the time period 0 to 2.5, which is colored by blue color, we can observe that the system undergoes a decay, after which it starts to revive after 2.5 oscillations, and then again starts to decay after 5.3 oscillations. So this is rather non-trivial in the sense that we have that the memory is decaying and reviving again. So we call this behavior as the shrinking and expansion of the hysteresis curve, which is the first time it has been observed in any physical system. Secondly, in order to quantify the memristive behavior, we introduced a quantity which is known as a form factor, and it is also a measure of the performance of the system in terms of the memory content, and it is represented by this formula, which is basically the ratio of area by perimeter square multiplied by 4 pi, so that it becomes a dimensionless quantity, and it is a nice parameter to quantify the performance of a decaying quantum system. So here I have plotted the performance of the single quantum memristor and the coupled quantum memristors. The straight line corresponds to the single quantum memristor because the rate of decay of the area and the perimeter square is the same, so that it becomes a constant. While this curve where we can observe the decay and rise corresponds to the coupled quantum memristors, and we can see that this performance actually crosses the single memristor case for some oscillations. And for more, as we plot for more oscillations, we can see more and more crossing of this figure of this form factor, and as compared to the single memristor case. So following this, we explore the entanglement dynamics using the concurrence, and what we find is that the concurrence also exhibits similar behavior, and it shows rise and decay along with sudden death of the entanglement, which is followed by a sudden birth. And it is shown in the inset of this figure, where we can see a finite amount of time in which the entanglement is 0. So these are the basic observations. And what we follow from this plot is that we want there are basically two questions. The first is that we want to answer where does the entanglement disappear, and secondly, we want to answer if there is a relationship between the entanglement in the coupled quantum memristors with the memristivity of the reservoir. So for this purpose, we try to investigate the interplay between entanglement and memristivity, and for this we plotted the concurrence along with the form factor. And what we observe is that the rise and decay of the entanglement coincides with the decay and rise of the form factor. So here, as you can see, the minimal of the form factor coincides with the maximal of the entanglement, and the maximal of the form factor coincides with the minimal of the entanglement. And this observation repeats itself as time goes on. So what we conclude from this plot is that entanglement and memristive dynamics follow an inverse behavior. So the loss of information due to a decay of quantum correlations shows up in the reservoir, increasing the memory, and vice versa. So following this non-trivial property, we also explore how the systems, how the coupled quantum memristors respond to each other's initial states, and for this purpose, basically how they can influence each other's dynamics. And for this purpose, we choose the input through the initial state, again by this qubit state, where we can change the state of the quantum memristor using either the real angle or the complex angle. So here, what I do is that I consider the two memristors and change the state of one of them, and I observe a change in both of them. So as you can see in these two plots, in the first plot, the quantum memristor 1 is realized in this state, and the quantum memristor 1 state is fixed in both of these plots, whereas the state of the quantum memristor 2 is changed from A to B. And what we observe is that this actually leads to a change in both of the memristors. And in the second figure, we see that the hysteresis signature of the second memristor is lost, but it can still retain the memristive signature of the first memristor. And this is a non-trivial result because in integrated neuromorphic architectures, we want that we can control the dynamics of one quantum memristor using the input applied to the another quantum memristor. The third non-trivial result is the relationship between the reversal between the hysteresis direction and the entanglement. So for this purpose, I've indicated the direction of the hysteresis for the first time period and the third time period of quantum memristor 1 and 2 both. So here corresponds the IV characteristics, and the second column corresponds to the voltage and current dynamics with respect to time. So as we can see, the quantum memristor 1 and 2 are initialized in opposite states so that their IV signatures are out of phase. So with time, we observe that the direction of hysteresis reverses, and it happens at time t equal to 3, time period equal to 3. So when we compare this time with respect to the time of entanglement, we observe that it actually happens. Okay, yeah, sure. I'll jump to the conclusion. So when we compare the dynamics with that of the entanglement, we see that this happens at the time when the entanglement reaches its maximum. So this is the basic result of this reversal in hysteresis direction. So following this, we propose how to move towards neuromorphic quantum computing, which are basically neural networks and analog classical neural networks have been proposed and realized using memristive crossbars. And we intend to do the same using quantum memristors, using architecture such as this, which allows scaling and nice controlling of the system using very few voltages. So the natural question is, can we use quantum memristors for neural networks? And this question was answered recently in a paper from Philip Walter, where they proposed the reservoir quantum computing using quantum memristors. So this was the architecture that they implemented, in which they used 3 memristors in parallel, not connected, in a photonic setup, where this area corresponds to the quantum neural network. This is the input to the system, and we have a simple readout mechanism with which we can train the system. And in this system, the quantum memristors provide nonlinearity and short-term memory. And the natural question is whether we can use entangled quantum memristors in such architectures. And because there is a possibility that interconnected memristive devices can provide better control of the architecture, and it can lead to much improvement in the performance that
Hello, Shubham. I think he cannot hear us. Shubham, can you? Oh, I think he has a connection issue. We'll wait for a minute and